Welcome to the session on Models 2. So we're going to have 3 talks. The first one is going to be presented by Noah. It's going to be on atomic gliders and cellular automata as language generators. Without further ado.
Thank you, Anthony, for the introduction. And yeah, hi, everybody. So my name is Noah, and today I will talk about our recent work, which is exactly atomic gliders and cellular automata as language generators. Some of us may be familiar with the concept of cellular automata, while some are not, but not to worry, we will set the record clear. So we will start with some background and origin of the cellular automata model. Cellular automata were introduced almost a century ago by von Neumann and Ulam as a self-reproductive biological system. It became popular thanks to the help of John Conway, who introduced Conway's game of life, which happened in the 1970s. One of the aspects that make it so appealing to other people is the fact that those kind of systems create the illusion as if something is living within the system. Those kind of object interaction within another assumed to be as a self-reproducing system, something that lives within this two-dimensional system. Next came Wolfram in the 1980s that considered the systems as a one-dimensional cellular automata in the simplest form, having only 2 states, black and white, and the radius of the system, which we will explain in more details in a bit, is only 1. Yet those seemingly very simple structure produce very unique abstraction and modification as an evolution over time. Meaning, whereas John Conway's had a 2-dimensional cellular automata that reproduce system that seems to be living, those kind of abstraction assume to have configuration that evolve over time, and this space-time diagram produces something that is pleasantly looking for a person, which make it more compelling. Over the decades, those kind of aspect and usage of cellular automata has spread across many domains. Most fundamental ones are biology as pattern recognition, epidemic spread, also in physics as lattice-based models and fluid dynamics, and even distributed systems, CA-like model, are considered for parallel systems, self-organizing behavior, and many, many more. But what might be surprising for some of us is that despite this wide range of application over the decade, cellular automata are still typically considered to be some evolution of space-time diagrams and not considered in a more formal aspect as we will usually consider them. So from a formal method perspective, we are usually considering what will be the language that the model can generate. How can we compare between different cellular automatas and what we will do about the behavior that cellular automata impose. And indeed, mathematicians pursued this direction as well. Hedlund, along others, pursued this direction from a mathematical foundation basis and described the systems as language. However, they consider what term to be language acceptors. They ask the question, what would happen if we start from initial configuration, whether the system would stabilize or non-stabilize, some kind of an accepting condition. So while closer in spirit to what we want to do, it's still insufficient for our purpose because we consider languages as generated by a cellular automata rather than being accepted. And from a formal verification perspective, we would like to consider the evolution from a set of initial configuration, what will be seen as the evolution grows. Meaning, we don't care whether specifically it would stabilize at the end, but we want to see what will be seen in the future. That way we can ask questions about safety, whether we will never see some unwanted behavior. We can ask a question about reachability, whether certain configuration would be reachable at the future, and so on and so on. So this is the roadmap that we have for this presentation. We will start with a very high-level description of the cellular automata. I want to create some kind of motivation and introduction to the model and to allow you to have some kind of visual simulation of what to come. Next, we will use this definition to understand the gap that we try to cover, which we did by introducing the glider as a semantical unit. We will get to that and conclude with our main contribution and the dynamic of the pattern and some conclusion for future works. So we consider an infinite line indexed by the natural indexed by the z numbers by all the indexed, meaning to infinity and to minus infinity. And each of those states is a process. Each process holds some kind of a value, could be seen as a state that it has, and usually can be considered as some color. As we saw with Wolfram, it was black and white. In here, let's assume it's pink and blue. So given this infinite line, let's consider some finite fragment and see what happens. So in this finite fragment, each of them is affected and evaluated based on the local interaction that it has, meaning every process has some kind of a neighborhood that determines what would happen in the next iteration as the configuration evolves over time. So if we consider only immediate neighbors, then it could be seen as a neighborhood of radius 1, and that will be the entire neighborhood. But in general, unlike classical elementary cellular automata, we consider systems that can have arbitrarily large radius, any natural number. And so it could be r equal to 2, r equal to 3. It all allows under our consideration. But to keep the example a bit simpler, we'll use r equal to 1. The evolution is defined by some lookup table. This lookup table determined in a deterministic manner what would happen, meaning if we have r equal to 1, meaning every neighborhood is of 3 cells, then the lookup table tells us, given a neighborhood, what will be the next state. So we note that, for example, this is the neighborhood of the middle cell, meaning those 3 current values would determine what will be that value in the next iteration. And we have a neighborhood that the neighborhood set is defined and fully deterministic, meaning although I show here only partial of them, you could assume that for any feasible neighborhood, any such set, there will be a value that dictates what will be the next step. So if we look on this evolution, the processes move one step at a time, and you can see that each of them looks on the neighborhood and look what will be the next steps. Now, although this presentation seems to be in a linear order, in essence, all of that happens simultaneously for all these infinitely many processes. So what would be is that a simulation would be something like that. That's one iteration. Given a configuration, the next one will be as follows. And so if we do that and consider infinite duration of by infinite configuration that evolve over time, what is being considered is actually the space-time diagram. It creates some kind of a visual representation of what to see. Now, shifting back to the classical cellular automata, such a transition would be something like that. Starting from an infinite configuration with only one black cell, then following some deterministic rule, apply something that is way more impressive than one might expect, given the deterministic and the entire variant. This is one of the rules that Wolfram introduced, creating the Sierpinski triangles, and we will see how everything is connected. So, before proceeding, let me fix our setting. What we consider is a one-dimensional cellular automata with a regular set of initial configuration, deterministic transition relation, and the natural question that comes to mind is that it looks very much similar to regular model checking. And so it leaves another question open. What exactly is being evaluated in this procedure? What exactly determines the behavior of such a system? So let's look on a classical example from regular model checking, the token passing protocol. In the token passing protocols, we have some finite yet fixed number of processes. Assumingly, classical variant is that the left most process has the token, and each iteration, the token is passed to its right until reaching the finite location, because we assume finite number of steps. So, crucially, this assumes the finiteness of the system. If we will try to implement the same thing for a cellular automata, then we lose what makes it regular model checking, because cellular automata are on by infinite configuration. Thus, this evaluation would never be actually done, because we could always continue more and more and more. So this already puts us outside of the frame that regular model checking imposes. Yet, to explore the intuition and the expressivity of such a model, we introduce a new type of protocol, what we term the two captains protocol. What we said is we have one red captain and one blue captain. At each round, each of the captains recruit a new player to their team. Let's assume that the red is spread to the right and the blue is spread to the left. So, turns are progressing and the rounds are progressing as well, and in each direction they maintain an equal number of red and blue. Now, although the pictures are very nice, we can also do that with the formal model that we have. As a cellular automata, we can consider that to be initial configuration with only one blue and one red cell. At each step, each of them recruit one new player to the associated direction. So, it is important to note that in this perspective, each row, each bi-infinite configuration, is the configuration under consideration. And unlike classical languages, when we say that a word will be the sequence of action we pursued, in this perspective, each configuration can be seen as sliced out and being a word in the language that we create. So, in a bit more details, what we do is kind of a projection. We keep only the active cells. Those that yet to be chosen could be assumed to be idols or something like that. But we look on the different ones, and each time step produce one word to the language. Looking on the overall observable configuration introduces a new language, which is the language of R to the power of n, B to the power of n, assuming red and blue for R and B. This already is a context-free language, which is not regular. Now, the key point is that these formal aspects created only by the local interaction that the system imposes. We started with one initial configuration. We impose only deterministic local rules, nothing that assumably create another power or memory to the model. Yet we exhibit something that is more than regular abstracts. So, if we view cellular automata language generators from this new perspective, what becomes the question is, how do we define the behavior that creates the semantic? How do we make sure that starting from the semantic unit and reach out to the language that we actually generate? What will be the unit that creates this kind of relation? This is where gliders comes into consideration. So first, that will be the sum up of the intuition. I know it's a bit high level. The paper is full with formal definition for all of you that might consider, but I wanted to make it clear and intuitive for you. It's what to come. So we turn now to the second part of the gliders. Very intuitively, very high level, I want to introduce some kind of vocabulary. How can we discuss this unit of semantics that create the languages over time? So we want to create something that represents it. Gliders as a term were already used in cellular automata literature. Usually what they mean is some kind of multi-cell variant that reappear in the system under some shifting periodically over time. But those kind of definition varies between paper to paper, and we wanted to make it much cleaner and more explicit to our requirement. So what we took is a glider, what we term an atomic glider, which is a single cell that moves across the grid in a constant manner. Let's see what it means. So we track atomic gliders. It's a one-cell carrier that moves across the grids, and we ask whether the local rules, those kind of transition relation that is deterministically defined, imposes some kind of a shifting across the board. So formally, this intuition is creating glider as a pair. Glider means to have some kind of a sigma, a value, or a state, could be the colors that we saw earlier, and it should have a velocity. Once again, it's important to note that unlike the elementary cellular automata of rule forms, our radius are not determined to be between -1 to +1, but for arbitrary large r. For example, in here, assuming that the radius could be large enough, then our local interaction, the formal rules, could imply that some kind of transition moves 2 steps to the right, 3 steps to the right, depending on our neighborhood. And so we create some kind of relation between them. Okay. Any questions so far? Okay. So, this perspective in gliders is not introduced in terms of, let me rephrase it. These gliders, in essence, allow us to create some kind of a semantical relation between 3 components of the system. What we have is set of gliders, set of initial configuration, and the language. So, given a set of initial configuration and a set of gliders, one can reconstruct what the generated language is by the cellular automata, because those gliders are defined by some kind of the local rule function. Respectively, assuming that the CA-generated language is glider-expressible, then we could do the other direction and to create a derivation of the set of gliders that, given a set of initial configuration, imposes the language in question. So there is kind of a relation that helps us to show what languages and what set of gliders allow for the expressivity results. Now, so far we talk about gliders in isolation, but in reality, when we want to talk about expressivity languages, we want to look on set of gliders that interact simultaneously. So let's consider this aspect. We start with initial configuration with 1 blue cell. Now assume that this value, the blue cell, has 2 gliders that are associated with it. One with velocity 0 and one with velocity +1. So, as every turn progresses, the gliders, in essence, spread across the board. Because even though some of them may be adjacent or even overlapping, they agree upon this decided state on the next step. Because if this cell wants to be blue and that cell wants to be blue, then although both of them would imply blue here, it's non-contradictory because they agree upon the next value. So now, if we add 2 more cells, we consider now also the red to be a value, and it also has 2 velocities of its own. The coordination between the 2 of them in reality create what we saw earlier as the 2 captains protocol. So we started with something that is well defined, followed by the gliders, and it's very important to understand that no non-determinism occurred here. Everything is fully defined. Initial configuration in that part is only 1. We have only 4 gliders that follows precisely from the local rule interaction. Yet the observed behavior creates expressivity that might be surprising, since we came from the aspect of regular model checking, which preserve regularity and not context grammar. So, if we consider many gliders that evolve together at the execution, we might want to understand what will be the languages in question, what will be the expressivity result of such a system. So, given a set of initial configuration and gliders, we get a CA-generated language which could be quite expressive. How expressive? That's exactly the point that we want to explain. So, we started with regular initial configuration, deterministic local rule, and we already saw before that observed languages are not necessarily regular, as of the AN, BN. But those kind of aspects can be even more expressive, because although this is already shown, by very similar aspect of application of the gliders in connecting with one another, meaning without an isolation, but rather a set of such gliders, we can impose much more complex languages as such. This one, still starting with 1 initial configuration. That one has 1 red, 2 blues, and 1 purple. And a set of gliders. Now, this set of gliders create a language which is a to the power of n, b to the power of 2n, and cn. That one is already more than Conrad's free grammar. And this kind of relation still maintained, because what happens here is the blue preserve all occupied position by the 0, and the +1, -1 allow it to spread to its sides, creating 2 new occurrences at every iteration. For the additional one, because in a sense, it could be seen as if the blue pushed them aside, they need to be moved 1 cell to the side to maintain the number of occurrences, and additional one that allow them to create a new value. So in each step, both A's and C's create 1 new iteration, while the B's create 2 new iterations, maintaining this kind of AN, B to the power of 2n, C to the power of n.
Can you notice that one gives you, like, one spreads the blue and the other one spreads the purple?
Sorry, I didn't follow.
No, because like you have several gliders.
Mm-hmm.
Can you not have 2 gliders that maybe coins collide or something?
Yeah, so that's a great question. I didn't discuss it in this presentation, but in reality for our paper we introduced a partial order between the gliders, and then they impose something else. But in here we show that even without the complex part, it's already observed something way stronger. But a great question. So very generally, what we consider in essence is a family of systems of wi to the power of ei in some n, which is wi's are non-empty words over some alphabet, and ei's are some non-negative linear expression, which allow us to create languages such as those that we saw before, but so many others as well. And those kind of expressivity is way even context-sensitive languages, still allowed by something that assumingly is finite, regular set of initial configuration, and a deterministic rule function. So, if we want to summarize what actually determines the expressiveness of what to come. So, we know it's not only the local interaction by itself. It's not only the initial configuration by itself, and it's not even the glider by themselves. It's a coordination of the 3 of them that allow us to determine the expressivity to come. So the objects are the atomic glider, a semantic unit, because in essence they create the alphabet of this language. The second one are the velocity and the partial order. As mentioned briefly earlier, we want to understand how far away each of them spread, what will be the relation between each of them as time proceeds. And those kind of relation imposes structure that can be very much complicated and induce some languages that don't behave the way that one might expect. And lastly is the initial configuration. So now we want to do some kind of a reality check, because there are also boundaries. We do able to describe many languages, many expressivity results, but if we want to define what can't be done with those gliders, then the first one is that there can't be no global synchronization, meaning each of them has local interaction. The knowledge is determined by the neighborhood. It can't be that 2 separate locations in some way create some kind of a lockstep and synchronize what they are doing, because the information is bounded to the area. The second thing is no unbounded choice or some kind of non-deterministic. Everything is deterministic. Everything is well-defined. Nothing creates something in between. So some models that create some kind of noise or non-determinism cannot be generated by such gliders. And the last thing is that there is no hidden memories. What we see, the configuration as is, the relation as the neighborhoods that imposes, that's what the model has. There is no hidden memories that can produce something else. There is no cache, there is no heap, there is no other information. And so those limitations, although limiting the system, are semantic limitations that come from the model under consideration. So let me summarize our main contribution. This is a very brief summary of our paper, but just to give you a bit of a feeling. So the first one is the semantic notion. We introduce what atomic gliders are. As we mentioned, gliders in the cellular automata community are widespread and unfortunately not much of a consistency between the ideas that introduce. So we wanted to take the core idea of what do contain glider as appear in the literature and to create the semantical unit as simple as possible. But it's important that atomic, it's not because it's necessarily the simplest, but because the semantic by itself cannot be even more refined, as it's a single cell that moves across the cell, determined by the local rule function. Secondly, we provide a language theoretic result for cellular automata as language generators. Instead of reasoning directly on the space-time diagram that the cellular automata imposes, we study the languages that are being induced in the observable glider domain. And the third, within the framework, we introduced a new expressivity results. Because, as we mentioned earlier, some mathematicians did consider the model, but usually, in order to make it reasonable, they considered a finite lattice rather than by infinite configurations, which maintain the expressivity of the initial configuration under consideration. Meaning, if you only want to stabilize and stuff like that, then you cannot create more expressivity than the one that you introduced in the beginning. Yet, in our results, the fact that we have the initial configuration that are regular, the set of deterministic rules, which in essence can be seen as kind of a transducer that maintain the regularity, still allow us to express something that is way more expressive. As we saw, we contain context-free grammar, context-sensitive grammars, and even beyond. So, some outlook and future works. So, the first thing is the verification-oriented abstraction. As we said, gliders are semantical units. So, one may consider from the verification perspective, what will be the way to reason about them, to create something that distributed system can be reasoned about in an infinite distributed system across time and across infinite domain. And the natural question will be, first of all, decidability. Understanding which properties of such system with the glider semantics, with their unit, can be algorithmically checked. The second thing is learning. If we want to learn such a system, how can we infer the system? How can we learn the system? How can we do that without knowing a priori knowledge about the system in question? And finally, there is an abstraction refinement. Using glider as semantic building, this allows us to reason about the system that can be composed or refine the capture richer behavior, because as we saw, it's very much a building block. It's just one cell that moves across the cell, across the grid. The information is given by the local rule function. Yet, the structure within it, as mentioned earlier, has a partial order, has a refinement, has a reconstruction, and also the variation from a system could be even more refined and more abstracted to languages with more expressivity results. And by that, I will conclude my presentation. I'll be happy to answer any questions. Of course, you could also reach out later on, and I would like to use this stage to also mention my upcoming initiative. Together with Andoni Rodriguez, we introduced the workshop about post-AI formal methods to take place at AAAI this year. And we hope to get it around as to represent the formal methods in the AI world. So that's pretty much it, and thank you very much.
I think we have time only for one question. So anybody who has questions? Okay, so.
And of course, any other question, you are more than welcome to come by and we can chat.
Thanks for the great talk. It was super interesting. Did you also think about two-dimensional, like automata, how the languages look there? Does it make sense to ask that?
So it's somewhat of a question. I would say Because if we want to look in the visualization that comes across the time, if you do it in two-dimensional, then in reality you create some kind of a cube of information that proceed. So although it has some kind of an interesting behavior, the initial idea came from the elementary cellular automata of Wolfram's that seemingly create something that is pleasantly and well-behaved, yet very much complex. But I don't think that we actually checked much about the two-dimensional. It's a very interesting question. So yeah, sorry I don't have an answer, but yeah, it's a great question.
Okay, so I guess, well, I guess you can set it up first maybe. Can I just maybe ask a super quick question?
Of course.
I think you can apply some techniques from regular model checking to analyze this, right?
Precisely, yeah. This is an idea that is already in progress as a future work.
Yeah, I mean, quite a natural thing considering Dana's background. So she did a bit of work on RMC. Okay, so thanks again. Yeah.
Thank you.